Alright, 10 things. 10. Let's see if you make it to number 1. Number 10. Wow signal. 1977. A radio telescope in Ohio called Big Ear was running on autopilot, scanning the sky and printing data onto long rolls of paper, columns of numbers and letters representing noise from space. Most of it was exactly what you would expect. Background hiss, static, nothing. Then the printout kicked out a sequence that did not fit. A few days later, astronomer Jerry Amon picked up the paper, spotted the spike, circled it in red ink, and wrote one word in the margin. Wow, that word outlived the telescope. The burst lasted 72 seconds. It was narrowband. One thin frequency, not the smeared mess you get from natural sources, and the frequency it sat on was 1420 megahertz, the hydrogen line. Hydrogen is the most common element in the universe. If you wanted every civilization with a radio dish to hear you, that is the channel you would pick. The spike was 30 times louder than the noise around it. Clean, tight, deliberate looking. It never came back. Telescopes aimed at that patch of sky for decades. Nothing. Later analysis suggested a cold hydrogen cloud hit by a magnetar flare could produce a similar spike. A comet hypothesis floated and sank because it did not match the telescope geometry. Instrument error looked unlikely because the pattern was too sharp for a glitch. Nobody has explained it. One burst, one printout, one red circle, and then silence for almost 50 years. Number 9. Lorimer burst. In 2007, a physicist named Duncan Lorimer and his student David Narkovich were doing grunt work. Combing through 6-year-old data tapes from the Parkes radio telescope in Australia, the kind of work that usually finds nothing, they found something. A single pulse, 5 milliseconds long, buried in data from 2001. For that sliver of time, the burst was brighter than anything a single point in the sky should produce. The dispersion pattern, meaning the way different frequencies arrived at slightly different times, told them the pulse had crossed a staggering amount of intergalactic material. Working backward from the dispersion, the source sat billions of light years away. Whatever produced it happened before Earth existed. 5 milliseconds. Enough energy to outshine galaxies. From a source so far away we cannot even confirm the host galaxy. Lorimer called it a fast radio burst. The name stuck. And the question it left behind stuck harder. How does something that brief carry that much power, and what fires it? Number 8. Repeating fast radio bursts. The Lorimer burst was a one-off. Many of the fast radio bursts found after it were also one-offs. Fire once, vanish, leave no forwarding address. Those could be freak accidents. Explosions, collisions, one-time catastrophes. Then some of them started coming back. One source, cataloged as FRB 121102, flashed again and again from the same spot in a dwarf galaxy 3 billion light-years out. Another switched on for a day, went dark for 16 days, then switched back on. A third cycled through 3 distinct brightness states every hour, like it was running through a program. Regularity, periodicity, mode switching. These are words that make engineers sit up. Random explosions do not have settings. Magnetars cover part of the explanation. These are neutron stars with magnetic fields strong enough to crack their own crusts, and when a crust breaks, the energy release can mimic a fast radio burst. In 2020, a magnetar in our own galaxy proved the connection by producing one in real time. But magnetars do not explain the mode switching. They do not explain the 16-day cycle, and some repeaters show a downward frequency drift. Each consecutive pulse slides lower in frequency like it is being dragged down a ramp. No simple physical model predicts that shape. It looks like a signature stamped into the burst itself, and nobody agrees on what is doing the stamping. Number 7. 234 synchronized stars. In 2016, astronomers Ermanno Bora and Eric Trottier at Laval University in Quebec published a paper that most of the field did not want to deal with. They had analyzed the light curves of 2.5 million stars from the Sloan Digital Sky Survey and found 234 that appeared to blink at the same rate. Not similar rates, the same rate. Spread across widely separated regions of the galaxy, stars do not coordinate. Each one fuses its own fuel, spins at its own speed, lives and dies on its own schedule. 234 of them pulsing in sync is like 234 strangers in different countries tapping the same rhythm on a table at the same moment. Bora and Trottier raised the possibility of a technosignature, something artificial modulating starlight on purpose. The backlash was immediate. Other teams re-examined the data, hunting for processing artifacts, selection bias, calibration errors. Some oddities survived the scrubbing. The timing held across different telescopes and observing conditions. Natural explanations exist. Maybe a rare stellar chemistry produces a common oscillation. Maybe an interaction we have not cataloged nudges certain star types into alignment. But nothing published so far reproduces the pattern convincingly. If the sync is real, either stars interact in ways we never measured, or something coordinated 234 of them at once. Neither option is small. Number 6. The Space Roar, 2006. NASA floated a balloon called Arcade over Palestine, Texas. It carried 7 radiometers cooled to 2.7 Kelvin, nearly absolute zero. Swung and climbed to about 120,000 feet. The mission was simple. Listen for the faint radio glow of the very first generation of stars, the ones that lit up after the Big Bang. What the instrument heard was not faint. The cosmic radio background came in 6 times louder than every known radio source in the observable universe combined. Not 10% louder, not double. 6 times the total output of every galaxy, every quasar, every gas cloud the models account for. The team spent years checking for instrument error, atmospheric contamination, interference from the Milky Way. They ruled out one source after another. The signal was real, and it came from everywhere at once. We have cataloged the radio output of the universe fairly thoroughly. Stars, galaxies, active nuclei, hot gas. Add it all up, and you get a number. The Arcade measurement was 6 times that number. Whatever is generating it, nothing in our inventory can account for the volume, and it has been pouring in from every direction in the sky. The roar also created a practical problem. It is so loud that it buries the faint signal the instrument was built to find. The first stars are still hidden behind a wall of unexplained noise. NASA went looking for a whisper and ran into a scream. Number 5. The SETI at home signal. In 2003, millions of home computers were donating their spare processing power to a project called SETI at home. The software crunched raw radio data from the Arecibo telescope in Puerto Rico, looking for patterns in the static. Out of billions of candidates, one floated to the top. SHGB02 plus 14A. It sat at 1420 MHz. The hydrogen line. The same channel that made the WOW signal interesting 26 years earlier. It came from a patch of sky between Pisces and Aries. Within 1,000 light-years of that spot, there are no cataloged stars, no known planetary systems. It pointed at empty space. It appeared 3 separate times in the data. Each time, the signal showed a frequency drift of up to 37 Hz per second. That is the kind of shift you would expect from a source sitting on a spinning or orbiting body like a planet. But every time the telescope went back, the signal reset to the original frequency before drifting again. Planetary motion does not reset like that. Follow-up observations came up empty. The SETI at home team classified it as a cautionary tale. Probably interference, possibly a processing artifact. Definitely unconfirmed. But the location still nags. Empty sky, hydrogen line, 3 appearances. If something in that void is broadcasting on the one frequency the whole galaxy would be listening on, it picked its spot carefully. Number 4, the 44-minute pulsar. Picture a strip of radio data scrolling across a screen. A burst shows up. About 2 minutes of steady radio activity, then silence. 44 minutes of dead air. Then the burst returns. Same duration, same brightness. Silence. 44 minutes. Burst again. The pattern does not waver. Arrays in separate countries confirmed the timing. Not a local glitch. Not a satellite pass reflecting off the upper atmosphere. A source beyond Earth was checking in at regular intervals. Most transient radio sources tie to rotation. Neutron stars spinning fast enough to sweep a beam past Earth every few seconds or minutes. Those timescales are short. 44 minutes is long, too long for a normal pulsar, too regular for random eruptions. The leading ideas involve precessing jets, mass transfer in binary systems, or slowly rotating white dwarfs dumping energy in periodic bursts. Each model covers part of the evidence, none cover all of it. Relatives showed up later. One source repeats every hour and switches between 3 brightness states. Another was traced to a white dwarf orbiting a red dwarf 1,600 light-years away. A fairly ordinary system behaving in ways nobody expected. The sky keeps producing metronomes. Some of them will turn out to be physics we have not fully mapped yet. And some of them tick at intervals that make your brain want to assign a purpose, whether or not one exists. Number 3. Tabby's star. In 2015, citizen scientists combing through data from NASA's Kepler Space Telescope flagged a star that was misbehaving. KIC 8462852, about 1470 light-years out in Cygnus. Astronomer Tabitha Boyajian led the paper, and the star picked up her name. The problem was the dimming, planets passing in front of a star block roughly 1% of its light, and they do it on a schedule. Tabby's star dropped by as much as 22% at random intervals with no repeating pattern. 1% is a planet, 22% is a wall. The speculation was immediate and loud, a Dyson swarm. So meaning artificial structures built around a star to harvest its energy would produce exactly this kind of signature from a distance. Irregular transits, deep dips, no periodicity. The internet seized on it. Tabby's star became the alien megastructure star overnight. In 2017, new dips arrived and observers caught them in real time across multiple wavelengths. The data showed that blue light dimmed more than red. A solid structure blocks all colors equally. Dust does not. Fine particles scatter shorter wavelengths more than longer ones, so the megastructure hypothesis is probably dead. But the dust answer comes with its own problems. The volume of debris required is enormous, and century-old photographic plates show the star has been slowly fading for over 100 years. Whatever used to orbit Tabby's star was destroyed. So what? Violently enough to produce wreckage that dims the star to this day. What did that and when are still open questions. Number 2. The Galactic Center Transient. September 2002. The Very Large Array in New Mexico was aimed at the center of the Milky Way, one of the most violent and crowded patches of sky a radio telescope can point at. Deep in the data, a sharp, repeating pattern showed up where nothing orderly had any business being. 5 radio bursts at 330 MHz. Each one lasted about 10 minutes. The gaps between them were exactly 77 minutes. Same brightness, same duration, same spacing. 5 in a row. The source was cataloged as GCRTJ 1745-3009. Researchers searched for it in X-ray data and found nothing. Gamma-ray archives, nothing. Infrared? Stoit nothing. Whatever this thing is, it appears only in radio and only on its own schedule. That narrows the options fast. A typical pulsar radiates across the spectrum. A flaring star leaves a heat trail. Binary collisions spray debris at every wavelength. This source punched through in one band, blinked 5 times with mechanical regularity, and went quiet. It showed faintly in data from 2003 and 2004, then disappeared. The best guess is a white dwarf pulsar, a slowly rotating dead star whose radio beam sweeps past Earth every 77 minutes. It is an elegant idea and nearly impossible to confirm when the source barely speaks. 5 precise pulses from the heart of the galaxy. No match at any wavelength. A source that seems to have better things to do than repeat itself for our benefit. Number 1. Proxima Centauri signal. Save the nearest for last. Proxima Centauri sits 4.24 light-years away. In stellar terms, it is standing in our driveway. In 2020, the Breakthrough Listen project was monitoring Proxima with the Parkes telescope when a narrowband signal appeared in the data. Narrowband is the key word. Natural radio sources like stars, gas clouds, and magnetospheres smear their energy across a wide range of frequencies. Thermal physics is messy. A signal squeezed onto one thin frequency looks the way an engineered carrier wave looks. The kind of thing you would use to carry information. The frequency was 982 MHz. It showed up during observations of Proxima and vanished when the telescope swung away. It lasted long enough to notice, and then it was gone. The team designated it BLC-1, short for Breakthrough Listen Candidate 1. The reaction was controlled on the surface and electric underneath. This was not an abstract signal from across the universe. This was a narrowband spike from the star next door. Follow-up analysis cooled things down. Some engineers found characteristics consistent with terrestrial interference, possibly a harmonic from local electronics near the telescope site. Others pointed to spectral features that did not fit simple interference models. No consensus emerged. If BLC-1 was real, it would be the most consequential detection in the history of science, the nearest star, producing a carrier wave. If it was a piece of equipment humming somewhere in Australia, then we learned how thin the line is between a historic discovery and a false alarm. And that might be the most important thing any of these signals teach us. We are not very good at this yet. Our instruments leak, our planet is noisy, and the difference between hearing a neighbor and hearing our own echo comes down to details we are still learning to measure. The next signal could be the one that settles it, or it could be the one that fools us again. Either way, somebody has to keep listening.